Welcome to lecture 11. So today we will start with information theory. I am skipping KL expansion for the time being. That we will do during detection of signals. So our understanding of random variable, we will start with say discrete random variable. That is the simplest situation with probability mass function. So we can visualize a discrete random variable as a map from some probability space to the real line, but only to some discrete points. And let us assume, to begin with, discrete means let us assume some finite random variable. So some finite number of points. So let us say that this map. So let us assume that there is some probability mass function. So x follows that probability mass function, say px. Okay. So if the random variable takes values say x1, x2 up to say xn, we say that they are having corresponding probability p1, p2 to pn such that summation of pk, k is equal to 1 to n is equal to 1, and all of these values are greater than equal to 0. All the values are greater than equal to 0, less than equal to 1, of course. So when we discussed about different moments of a random variable, we basically did a combination of the values the random variable takes along with the probabilities the random variable assumes. Be it discrete random variable or continuous random variable. When I write something like some moment like this over the entire real line, when I write x dfx, so it can encapsulate both discrete and continuous. Here we are mixing two things. One thing is the value the random variable assumes, another is the distribution function or density function, mass function, etc. However, there is this side, which is the probability side, which is not separately quantifiable by these moments, whether you take this moment or this moment. Whatever moment you take, be it first moment, second moment, these moments, they don't quantify the randomness or the probability measure which is inherent in the probability space. That is not quantifiable by these moments because the value is embedded. Sometimes we want to quantify the probability only, not the values the random variable take, because sometimes the random variable value assignment is kind of ad hoc. You can this is for a game of gambling. It is basically the assignment given by the owner of the gamble. So it is kind of ad hoc, but something which is really fundamental, really inherent, is the probability values, the the measure, which is induced in the random variable definition, which is coming to the distribution function. Okay, so if we want to really know about the probability space and its corresponding induced measure, moments are probably not the right functional. We need something else. So we need something which I am going to discuss today, which is called the information content of a random variable. So before going into random variable, we can start with the events actually. So the construction of information. So let us go back to the probability space, to the sigma algebra. So if you observe two events, suppose this is one event, this is another event, so we can say that those events are elements of the sigma algebra, or we can write those events are subsets of the sample space. Okay, and you have the corresponding probability values, the measure defined for those events. Okay, so we may ask that when we are performing the random experiment, the probability experiment, we don't know whether this event is happening or this event is happening or some other event is happening. That we don't know. Now when we will be surprised, and if we want to quantify the surprise, how do we get surprised? What makes us surprised? So I can talk about different gambling experiments to measure, to counter, like have some quantification of the surprise element. For example, you are tossing coin, okay? So you are tossing coin and you are tossing the coin, say n number of times. Say n is equal to say 100. So out of those 100 coin tosses, if you observe say around 50 heads, so suppose you observe 51 heads and 49 tails, will you be surprised? Probably no, because that is what you expect. It is fine, it is obvious. But what will happen, so this is suppose one event, so out of the n is equal to 100 coin tosses, this is one event, this is say event A, one sequence, okay, out of those 100. And the second event which you may observe is say 99 heads, one tail. So this is very much unlikely, because if the coin is unbiased, out of the 100 coin tosses, this is very much unlikely. So this becomes some information. I can give you one more example. Suppose there is a game called poker. So everybody is given like initially 3 cards, and then there will be 5 cards in the on the table. So which you will not 3, initially 2 cards, then 5 more cards. So out of those 7 cards, you have to make some combination of 5 cards, and which player is getting the best card, he will win, that person will win. Now when there are 52 cards, the probability that you will get some like combination of different suits, heart, club, diamond and spade, and different kind of numbers, that is more obvious. But which are more surprising? Suppose you get say one set of ace, king, queen, jack and 10 of the same suit, suppose of the spade. If you get such kind of set, that is more surprising, and that is some information, that is like something which people want to know. Not the common hands, not the common hands. Suppose if you get some diamond of 2 and 7 and then spade of 5 and 8 and some club of say Q, this is less surprising, because this is from the same suit. Suppose this is suppose some offsuit, and this suppose something like that, okay? So this is less surprising, this is more surprising, because this is a unique combination which does not often quite normally. So on which this surprise depend on? It depends on the probability, like what is the probability of occurrence of this kind of suit or this kind of not interesting hands, or here in the coin toss experiment this kind of situation where 51 and 49. So what are the total number of situations this combination will arrive? What is the total number of combinations? So you can see that 51 can happen in 100 C 51 cases, okay? The rest will be tails. So this is a huge number. This number is basically 100 factorial by 51 factorial, 49 factorial. How many times this will happen? Only 100 times. So this number of like such events are much more. The probability of occurrence of this event is much less. That's why we are much more surprised with this kind of event. So the information, if I want to quantify, it has to do with probability. So like the less the probability is, we will say that the more the surprise is, or the more the information is. The more the probability is, we will say that the less the information is. So what is having the lowest information? We will say that if somebody says that the sample space itself occurred, obviously that occurs with probability 1. So that is not information. So if somebody says, okay, I tossed 100 coins and out of 100 there are some heads and some tails, so that does not say anything. So it is as good as saying that I have tossed only 100 coins, or out of the 5 cards it is like the 5 cards are one of the 52 cards. That is not information, that is the entire sample space. So that is like least information, it is trivial, it is 0. Okay. So like intuitively, information is quantifiable as some function of probability, but it should have some characteristics. So information should have the following characteristics. So number one is if say probability of A is less than probability of B, then we say that the information of A, I write I as the information function, say some information function or information measuring function, this will be greater than information of B. Okay, information is 0 if the probability is 1. So for the entire sample space the probability is 1, and for that the information is 0 because there is no information, it is obvious. And information is always positive, of course, because we know that the information is a decreasing function, as we are seeing from here. So information is a decreasing function in the probability, is a decreasing function of the probability. So the maximum set or the maximum probability is 1, and for that the information is 0. Anything less probability has to be having information greater than that. So we can say that the information is always greater than equal to 0. Okay. And another thing is suppose two events A and B, they are independent. So these two events are independent. Then we say that information is additive. So the information that the joint occurrence of A and B will be the information of A and information of A and information of B. So information is added. Okay. So these four characterizations, from here we have to define some function such that we can quantify information. And Claude-Shannon, so there can be different functions, I don't know, but what Claude-Shannon did, he found out that the following function characterizes the information pretty well. So he derived that, okay, information as a function of P is suppose the probability of that particular event. If I write the information to be logarithm of, I take the logarithm with base 2, logarithm of 1 by P, this function characterizes satisfies all these conditions. Let us check quickly. So suppose P is equal to 1, so IP is equal to log of 1 is equal to 0, so 3 is satisfied. Let us check 1. So suppose say 0.3 or P is less than Q, so IP minus IQ is equal to say minus log or log of 1 by P minus log of 1 by Q, so which is equal to log Q by P, and Q is greater than equal to P, so this is greater than equal to log greater than log 1, which is 0. So clearly IP is greater than IQ. So it is a decreasing function of P. So 1 is satisfied. So 1 and 3 combined we can get this is 2 actually. Yeah. 1 and 2 combined we can get 3. So that is for any probability this is greater than equal to 0 obviously. And finally the 4 we can check again. So if A and B events are independent, then probability of P A intersection B is probability of A into probability of B, that is from independence we know. So now I of this P A intersection B, that is equal to log of 1 by P A intersection B, which is equal to log of minus log of say P A intersection B, which is P A into P B. and log of a product is basically sum of the logs, so minus log PA minus log PB, and this can be written as I of PA plus I of PB. So this is additive if the the events are independent. So clearly this particular function log of 1 by P, it satisfies all the intuitive conditions of information. So now from this event we can come back to the random variable itself. So suppose you have the discrete random variable. So the discrete random variable is having x, which takes the values x1 to xn with probabilities p1 to pn. So what is the measure of information of every occurrence? So x1 happens with probability p1, so we say that the corresponding information is log of 1 by p1. So this is the information, this is the log of 1 by pn. So if I ask that what is the average information of the random variable, so average information of the random variable, of x, so it has to be of course the expectation of the information of a particular value, so that pk. So this which you can write as summation pk ipk, and from Shannon's formulation if I write ik is equal to, this is k is equal to 1 to n, and if I take the Shannon's formulation it will be pk log of 1 by pk or minus summation k is equal to 1 to n pk log pk. So this average information or the expected information of the random variable, this is called the entropy of the random variable. I write it by hx. This is called the entropy of the random variable. X. And since this is done with the base, the logarithm is taken with the base 2, the unit of entropy is bits. So unit is bits. So if the base is taken as E, then it will be called nats, etc. But for like digital communication or digital electronics, this log to the base 2, that is the most convenient one. So it is the unit is called bits. So this, what is this entropy of random variable? Later on we will see when we will talk about the source coding and all. This is basically, the entropy is basically the average length in terms of bits, length in bits, which is required to describe the random variable. So this is curious because the average length, the random variable x, the average length does not depend on what value the random variable assumes. So our common sense is that it depends on the real number, the value. Not really. It depends on with what probability that particular value is taken. So this is one remarkable understanding, remarkable realization of Shannon, that the main thing, about information of a random variable or description of a random variable is not the value assignment, rather the probability of occurrence, and this entropy, which is the most important one. So this entropy we can compute for some simple random variable. So let us take some quick simple example. Let us take a Bernoulli random variable. So the Bernoulli random variable, so one coin toss. So define the random variable to be 1 with probability p, 0 with probability q is equal to 1 minus p. Okay, this is a head, this is tail. Okay, so now this value assignment does not matter. We will see that the entropy of the random variable is basically the expected value of the information content of the two events. So it will be minus p log p minus 1 minus p log 1 minus p. Okay. So what is the maximum value? Minimum value is of course 0, that will show in the next page. But if we try to plot it, say for different values of p, we will see that the value for if p is equal to 1, so the information content of that value is 0 definitely. Now what is the other value if say q is equal to 0? So what is 0 log 0? So that requires a little analytic understanding, because by itself 0 log 0 is undefined, but if we understand from the limiting perspective, so 0 log 0, this we can write as some epsilon log epsilon when epsilon tends to 0, isn't it? So that I can write as log 1 by n log 1 by n, so that I can write as minus 1 by n log n tends to infinity, where I can write n as 1 by epsilon. So now look at this, when n tends to infinity, log n is also growing definitely, but log n is growing at a much slower rate compared to n. So log n by n always tend to 0. So 0 log 0 we can fix to be 0. So when p is equal to 1, hx becomes 1 log 1 minus 1 log 1 minus 0 log 0. So the first element is 0, second element is also 0. So this is 0. Similarly, when p is equal to 0, hx is also 0. So this is maximized. You can perform the differentiation, it will be done from there. So find dhx dp is equal to 0. So that will give you the maxima. The maxima will come out to be at p is equal to half. So at p is equal to half, it will be minus half log half or like half log 2 plus half log 2. So log 2 is 1, so half plus half is basically 1. So at the midpoint, at say p is equal to half, it attains the maximum value, and at the two boundaries it attains the minimum value. So the minimum value is 0, this is say 1, this is say 0, this is p is equal to half, and the maximum value is 1 bit. So if the coin is unbiased, we say that 1 bit is required to describe the random variable occurrence optimally. For anything else, you don't need 1 bit per random variable, per assignment of random variable, isn't it? So this this entropy is having certain characteristics. For example, we can say that the properties of the entropy, properties of hx, we can write. So one is definitely hx is greater than or equal to 0. How to prove it quickly? So px is between 0 and 1. So 1 by px is between infinity and 1. Log of 1 by px is between infinity and 0. So px log 1 by px is between infinity and 0, and sum of that has to be greater than or equal to 0. Okay, so this gives you clearly hx is greater than or equal to 0. Now from entropy we can extend this idea to multiple random variables. So suppose, so then we need a few more definitions of this information when there are more than one random variables. So we'll start with joint entropy. So suppose you have two random variables x and y, okay, defined over the same probability space, but they are having different distributions, of course. So suppose it is having they follow the joint distribution. Right now I am working with discrete random variable or finite random variable. Later on we can generalize it. So suppose the joint distribution is pxy. Okay, so we can similarly define the joint entropy to be hxy as summation, and let us say the cardinality of x, the support set of x is like it assumes the value of x, so the support set of x is called the curly x, which is basically the values, the set of the small x's. So we can say this is for all curly x, and the support set of y, the random variable y is say the curly y. So we can say it is for all y in curly y. This is basically those numbers x1, x2, whatever xn. This is say y1, y2, ym say the values it assumes. So the joint entropy is basically the pxy, the joint distribution, joint mass function, log pxy with a minus sign, or I had to write 1 by. Now this is the joint entropy. In the same way we can define conditional entropy as well, because we know for these two random variables x and y, we know the conditional probability can be written as probability of say y given x can be written as probability of the joint probability divided by probability of x. Okay, so in the same way I can construct the conditional entropy to be say h of y by x. It is basically the average like entropy when conditioned over one instantiation of x. So if I do it over x, it is basically h of y, one instantiation of x. So which I can write as summation over all x's px h of y given x. Now this is entropy. This is not conditional entropy. This is entropy when one event of x, one value of x has been assumed. So that can be taken from the regular definition of entropy. So it will be equal to x given x px. This is a probability of y given that value which has been happened, y given y, log of 1 by p y given x. This I can write. So that can be extended as equal to summation over the two like domains. One is x, another is y. I can take the minus sign out, so it will be px py given x log py given x, and these two can be combined to get pxy, the joint, log py given x. Okay, so from these two definitions, conditional entropy and joint entropy, I can construct a chain rule of entropy for two random variables. So the chain rule can be written as, so I can connect the joint entropy with the entropy of one random variable and conditional entropy of another random variable. So my understanding is that, so what is this? This is on average the total information about the joint occurrence of x and y. So I expect that the average information about one random variable and average information about the like another random variable conditioned to the first, this would be kind of additive. That can be shown clearly from this construction. So I am doing it quickly. So hxy is basically summation over the support set of y, pxy log of pxy, which is equal to, I can write pxy, and this can be split with the condition. So px into py given x. So this is the mass function Py given x, this is the mass function Px. Now log of a product is sum of logs, so I can write that as Pxy log of Px plus log of Py given x. This is for x, this is for y. So now I can take them separately. So this is Pxy log Px. This is Pxy log Py given x over x y x y. Now what is this? This is like this particular thing is independent of y, so it can come out. So this is for x, this is p log px, the rest sum is over y pxy. So if you sum pxy over y, what do you get? You will get the marginal of x, so that you will get. And what is this? This is the conditional entropy hyy given x. So this thing is the marginal of x, so this will be written as summation x given x in x log px, and this is px plus hy given x. The first term is hx, so hx plus hy given x. So I can write in this way. So we can visualize this chain rule or the relationship between conditional entropy and joint entropy from a Venn diagram kind of like pictorial viewing. So I can write in this way, just like in set theory or in probability theory, you construct the Venn diagrams for quick visualization and quick understanding. So I can think of that, okay, suppose this is a random variable, this is the entropy corresponding to the random variable x, so let us write this to be the hx, and this is the random entropy corresponding to the random variable y, so this is the hy. So hy is basically this entire area, and hx is basically this entire area. Then hxy, the joint hxy is basically the complete area. Okay, now what is so hxy is the complete area, that is equal to hx is this area plus hy given x. So hy given x is basically this area, this entire area, which is the additional. So x is given. If x is given, then whatever is extra in y, that is basically hy given x, the conditional entropy of y when x is provided. So the chain rule can be like observed quickly from this Venn diagram kind of visualization, and it can be extended not only for two random variables but for arbitrarily many number of random variables. Suppose we can take this page number 6, so we can take say x1 x2 say xn. So these are suppose a sequence of random variables, okay, and there can be overlap between the random variables. They are not independent random variables, there can be dependence. So sequence of random variables. So we can write the chain rule as the joint entropy of all those random variables will be equal to I can write as hx1 plus hx2 given x1 plus hx3 given x1 x2 plus like that, plus finally hxn given x1 to xn minus 1. So I can write like this chain rule. So what you can try, you can prove it using the joint distribution. So the chain rule of joint distribution using the conditional probabilities. So which you can do using like when I write x1 to xn. So this will be equal to basically probability of x1 into probability of x2 given x1 into like that xn given x1 to xn minus 1 So this is the chain rule of conditional probability. From there you can directly obtain this one. You can visualize it in this way also. So suppose this is x1, this is say capital X1, this is say capital X2, this is say capital X3, and so on and so forth. So you can add them, so you can visualize it in this way. So when you want to get the joint, so h of x1 is basically this area, the entirety of x1. H of x2 given x1 is basically this area, the extra of x2 excluding the area already covered under x1. x3 given x1 x2 is over. Whatever additional is there in x3, that is x3 given x1 x2. So by this way you can construct the chain rule, and this is a quick visualization by this Venn diagram approach. Okay. So after this we need a few more definitions, because one construction will be required, because till now we did not characterize the overlapping region of x and y, the so-called intersection region you can say. So to do that, then our construction of this entropy function or the average information, it will be over. So for that we need a couple of more understanding. So one understanding is called the relative entropy. There is another name of this relative entropy which is called the Kullback-Leibler divergence. KL divergence it is called in statistics literature. So this idea is like, it is not really between two random variables, rather it is between two distributions of the same random variable. Suppose you have a random variable x, and suppose it follows some mass function px. This is the true mass function, but you don't know the true mass function, so you estimate by some other mass function qx. This is some estimated mass function. Okay. So this Kullback-Leibler divergence basically computes the information theoretic distance between the two mass functions. So this is kind of some information theoretic distance, although it is not truly a distance. That's why it is called divergence. Distance means we will always say distance to be a matrix distance, so it should characterize, it should satisfy the triangle inequality, it should be symmetric, etc. This particular thing is not. So we can say this is information theoretic distance, but not truly distance, not really, between two distributions, here px and qx. Okay. So we define that to be the d is basically for the divergence between this p and q. We write like this, the double bar, and it is written as summation, and suppose both the distribution is having the same support, so x belongs to this, so the same support, px log of px by qx. Okay, clearly you can see this is asymmetric, so dpq is not equal to dqp, so they are different. Okay, because if you write dqp, it will be like the expectation will be taken with respect to q, not with respect to p, so they are not same. These two values are different. Okay, so it is not symmetric, it is not truly distance. So this particular but one thing is satisfied, that if px and qx are identical, then this value is 0. This divergence, scale divergence or relative entropy is 0. Okay, so what it can be useful for, Okay, for computing these things, another convention is that the 0 log 0 by 0 is 0. That is what is understood. And so we will take that 0 log 0 by 0 will be assumed to be 0. And also if you have some value like p log 0 by p, p log p by 0, this kind of scenario if arrives for some like if some assignment, if the corresponding probability under the true mass function is positive but under the estimated mass function is 0, then this will be assumed to be infinity. Okay, that is obvious. So where this is required in our understanding of multiple random variables, it will be required to understand whether two random variables are independent or not. So to understand whether two random variables x and y are independent or not, so if independent or not, so their joint probability, this is the true joint probability pxy, this is the true joint mass function. And if we assume that they are independent, so if we assume x and y are independent, then what will be their joint mass function? That joint mass function can be written as the product of their individual marginal probability mass function. So if they are independent, then this will be px into py, which I can write to be qxy. This is the estimated one if they are independent. So the corresponding KL divergence thus appearing, which will be equal to the true is pxy and this is the estimated, if that is true, if their independence is true, then this KL divergence, which I can write as summation over x and y, x and y, or I can write using two sums, that will be better, two sums. So this will be pxy log pxy divided by pxpy. This particular KL divergence between the true joint mass function and the independent joint mass function, it is called the mutual information between x and y. So there is a name, and this name is called mutual information. Now you can see that this mutual information is indeed symmetric, because ixy, if I write iyx, there is a semicolon in between. That is how it is written. So this yx is pxy py px, that is same, right? So that is same as ixy. So this is a symmetric function of x and y. So I can relate this mutual information with our earlier definitions of joint entropy and entropy, and that we will do next. So a relationship between these different terms, say between ixy, hxy and hx, hy, that we can establish next. That is ixy is equal to summation pxy log pxy pxpy. So I can split it into three different sums. So the first one is minus summation x log px. So marginal over y is gives you px. Check it, I am not writing everything explicitly. Y log of py and marginal over x of this is py plus pxy log pxy. So what is this? The first term is hx, second term is hy, and third term is hxy. Now I can connect these two and these two to get some other forms as well. So hx minus x given y. So hx minus hx given y and minus hy minus hy given x. These forms we can also make. Now these simple equalities, these simple forms, we can visualize using the Venn diagram which we have drawn earlier. So I am drawing it again to relate these quantities. Suppose this is the simple Venn diagram. This is for hx, this side for hy. So now I will show you that the entire thing is definitely hxy, the joint. Now this part is essentially hx given y. This part is essentially hy given x, and this part is your mutual information. You check. So from here I can quickly write all the relationship, like hx given y is essentially hx minus ixy. I can write like this. I can write as h of xy minus hy, isn't it? H of y given x can be written as h of y minus ixy is equal to h of xy minus hx, like that. So all the relationship between different entropy terms can be obtained from this Venn diagram only. You don't need anything else. What can be done next? Okay, we can get some more interesting inequalities of information theory. Before going into the continuous random variable, I should introduce some inequalities of information theory. For example, the positive non-negative property of the mutual information. That is one of the important result. But for this I need Jensen's inequality. I don't know whether you know Jensen's inequality from your calculus background. Let me quickly say that Jensen's inequality says that if a function is convex, f is convex, then expectation of fx is greater than equal to f of expectation of x. Just the opposite for concave. So if f is concave, then expectation of fx is less than equal to f of expectation of x. To get the visualization quickly, I can tell you like this, with just two, inductively you can develop them. So with just two values, suppose the random variable assumes two values x1 and x2, and suppose the occurrence is with probability of p1 and p2. Okay, so what is the expectation? The expectation value of this is in between, so which is say x1 p1 plus x2 p2. That is some value in between. This is ex. Okay. Now your function, the function value is fx, some value. This is some other value, fx2. So if I compute the expectation of fx, this side, this will be basically somewhere here at some point. Okay. So which is p1 fx1 plus p2 fx2. p2 is basically 1 minus p1, right? So it is a linear combination which is at this point. Now f of ex is basically the functional value of at that point. Now if this is convex, we know that the functional curve is always like this, so it will always lie below this straight line, so the corresponding inequality is satisfied. For concave it is just the opposite, obviously, so that will be the function of the expectation of x will be above. Now this I have shown you for just the Bernoulli random variable scenario. If you increase to any number of x1 to xn, inductively you can prove that. I am skipping that. What I am interested in, using Jensen's inequality for this concavity, I will prove the information inequality. Which says that the KL divergence between any two probability mass functions is greater than or equal to 0. So how to check that? So the proof is pretty simple. I can write that minus of d, p and q, which is equal to minus of, say, summation p, px log px by qx. So this minus can be taken inside, so this will become qx by px, so that will become px into log qx by px. So this is expectation of log qx by px, isn't it? So since this log function is concave, so expectation of log qx by px will be less than equal to log of expectation of qx by px. Isn't it? So this is equal to px cancels out, summation of qx is 1, so is equal to log of 1, which is 0. So d minus d is less than equal to 0, so d is greater than equal to 0, so hence proved. So this is information inequality, but from this information inequality I can quickly check that mutual information is positive, because mutual information is KL divergence. So my statement, my theorem, I can say that mutual information is always positive. Proof is obvious, because mutual information is nothing but KL divergence between pxy and pxpy, which is positive. From here I have seen that. So from information inequality I can quickly say that this mutual information is positive. Next I can get another theorem of another observation of entropy. So suppose you have a random variable x and its like support set is this. Okay, so this is the support set, and the cardinality of the support set is, say, this is some n or something. So if you define some uniform mass function to be 1 by the cardinality of the support set, this is uniform, so if this is 100, it is 1 by 100, then we know that the KL divergence between this ux and the px, which is the true probability mass function, it has to be greater than equal to 0 from information inequality. Now what is this? This will be equal to summation px log px divided by ux, that is equal to summation over x. So summation px log px minus summation px log ux. Log ux is 1 by this. So which is equal to, this is minus hx and this is equal to plus summation px, log of the cardinality of this summation px, and summation px is 1. So this is equal to log of cardinality of the support set minus hx, and this is greater than equal to 0. Hence hx is always less than equal to log of cardinality of x. So hx is maximized when all the outcomes of the random variable are equiprobable. So if you have some random variable that takes value into a set with say suppose it assumes values in this set x1 x2 to say x16. Suppose it takes 16 values. So this is your this cardinal x, this support set. So the cardinality is basically 16. So I say that the entropy of this random variable will be maximum if all the probabilities p1 to p16, if all of them are 1 by 16, then the cardinality will be maximum, and that cardinality will be log of 16, which is 4. Okay, so that we have already observed for the Bernoulli scenario also in our earlier discussion. So when you take the two probabilities to be equal up, you obtain the maximum value of the entropy, which is log of the cardinality. The cardinality is 2, so log of 2 is 1. That you have already seen. Okay, so this is the maximality of entropy of a random variable. So under uniform scenario, the random variable attains maximum entropy. Okay, quickly we can go through a couple of interesting results before we stop today. One result is called the say conditioning reduces entropy, or we can say that information cannot hurt. Information does not hurt. Yes. So we say that from the Venn diagram itself we can like quickly write this, that h of x given y, the conditional entropy has to be less than equal to hx. This is obvious, right? From this diagram, because we know h of x given y is nothing but hx minus I of xy, and I of xy is positive, so this has to be less than this. So what is the physical significance of this particular expression? It says that if you know about some random variable, if you know about any random variable, y, you have the information. So now if you are trying to estimate the random variable x, so what you are basically obtaining, you are obtaining the conditional entropy hx given y, because y is known, and this hx given y cannot be more than the entropy of x. So whatever random variable you know, when you are trying to find out the any other random variable, its entropy, it will be always less than its individual entropy. Okay, so this is one very intuitive result and obvious result, I would say. From here we can relate with functions of random variable as well. Actually I can talk about the Markov chain. Suppose I have three random variables x, y and z. Okay, I have written in this way. This is called a Markov chain. If z and x are independent conditioned on y, if y is known, then conditionally x and z are independent. So x and z are independent given y. So I can write the joint distribution function, joint density function of x, y, z in this way. Px, Py given x, Pz given y. So if y is known, z does not depend on x anymore. Okay. So from here I can from this chain rule I can quickly develop the conditional independence characteristics. So xz given y is nothing but probability of xyz divided by probability of y, and probability of xyz is this. So this is equal to px py given x pz given y divided by py. Now px py given x is pxy pz given y divided by py, and pxy divided by py is px given y into pz given y. So clearly you can see that x and z are conditionally independent. Okay, so it says that okay, so if z is say any function of this random variable, then always x y z which is equal to fy is always a Markov chain, because this fy cannot be dependent on x if y is already known. Fy is completely described by y only, right? Be a Markov chain. Now Markov chain is like both way. It is symmetric. Symmetric in the sense from here you can see that xz are conditionally independent. So it does not matter whether the flow is from x to y to z or z to y to x. So it is equivalent to saying z y x. That is also a Markov chain. This is also a Markov chain. So sometimes it is written as x both direction, y both direction, z. So it is also written sometimes. This is also Markov chain. Okay? So for this Markov chain, we have something known as the data processing inequality. With this I will conclude today. So which is called the data processing inequality. It says that if you have a Markov chain x, y, z, then I say that the mutual information between x and y is always greater than the mutual information between x and z. Okay. The proof is pretty simple. So the mutual information between x and the joint occurrence of y and z can be written as, so I can draw diagram, okay, x, y, z. This is a x, this is a y, this is a z. So mutual information between x and yz combined. So yz combined is basically this. This is yz. And mutual information between x and that is basically this area. This is mutual information of x with yz. So that can be written in two ways. One way is this plus this, another is this plus this. So I can write like that: mutual information of x with y. So mutual information of x with y is, I am drawing it here again. You relate them, okay? This is x, this is y, this is z. So mutual information of x and y is this area, plus mutual information of x and z given y. This is mutual information of x and z. So this area, mutual information of x and z when y is given, isn't it? I can write in the other way as well. So this is this expression. I can write in another way, that is mutual information of x and z. So I can visualize like this: x, y, z. So mutual information between x and z is this one, plus mutual information between x and y given z, that is this area. Now out of this you see that mutual information between x and z given y, this has to be 0, because from the earlier construction we have developed that they are independent. Given y, they are independent. So the Kullback-Leibler distance between divergence between this and this is 0. So that is the mutual information between x and z given y, isn't it? So x, z given y is nothing but the KL divergence between p x z given y and p x given y into p z given y, and this has been already established to be same. So this is 0. If that is 0, then I can say that I x y will be equal to I x z plus I x y given z. Now this is equal to this is greater than equal to 0. So if this is greater than equal to 0, then definitely I x y minus I x z will be greater than equal to 0. So I x y will be greater than equal to I x z. So if z is a function of a random variable, the like mutual information between any random variable x and a function of a random variable, that will be always less than between like with respect to the mutual information between the first random variable and the second random variable. So this is called the data processing inequality. With this I conclude today. In the next class I will be talking about like extending the idea of law of large number to the information theoretic realm, which will be called the asymptotic equipartition property. Now we are quickly moving towards our domain of digital communication, and after this AEP we can move towards continuous like random variable, and then we can enter quantization. So we'll talk about entropy coded quantization. So one more lecture for this asymptotic equipartition property, then we can move towards quantization. Okay. So please listen to all these lectures. Till then, goodbye.